So in this video, we're going to talk about performing a hypothesis test, a topic that one sees in statistics. And what we're going to look at is we're going to look at a one-tailed test is what it's known as. We are going to talk about a lot of other things in this video. This will be probably a little bit of a longer one because there's a lot to speak of. There's not a ton of computations, as you'll see. In another video, I will do a two-tailed test, but a lot of the information that you see in this video, I'll glaze over when I get to that example. So certainly start here if you're new to doing hypothesis tests. Okay, so what are we going to do in this video? We're going to perform a hypothesis test, and here we want to do the hypothesis test of some mean mu, and we're going to make an assumption here, and that's that we know sigma. And in real life situations, this typically, oftentimes won't happen, and we'll talk about what to do in that case. But for now, we'll assume that we know our value of sigma. We'll talk about formulating the null hypothesis and the alternative hypothesis. We'll talk about one-tailed and again two-tailed alternative hypotheses, and then we'll also talk about the decision rule. Okay, so one thing to discuss before we get going here is we're going to use the Central Limit Theorem, and this is one of the uses of the Central Limit Theorem. I mean, again, that's why it's named that. It has such a broad application across statistics. If you forgot the Central Limit Theorem, definitely do go take a quick glance at it because it basically says what we're doing is allowable, it's valid. Okay, so we want to use the following assumption for a hypothesis test. And again, this is about a mean mu and a known sigma. So this is the key result here. And the idea is that the sampling distribution of our mean, x bar, that has a normal distribution. Okay, we can assume that things are normally distributed is what we're doing. And under, certain conditions, again, this is what the Central Limit Theorem says, and we're going to assume that we can apply it. So again, if you've forgotten about the Central Limit Theorem, definitely go take a look at that. So a remark here. Now, the hypothesis test that we're going to use is what's known as a probability value hypothesis test. We will also do, in a separate video, I'll talk about some other tests as well. So this is going to be known as the probability value approach or simply the p-value approach. You can probably skip that last part. Okay, so this is the probability value hypothesis test, and this is going to be the recipe. So let me go through these really quickly. So part one, we've got our setup. So what we're going to do is we've got some population parameter of interest. There's something that we want to measure, right? There's something that we want to get information about. And again, this is something that we can quantify numerically. Okay, well, we've got this thing we want to look at. Well, from there, we're going to form our null and our alternative hypotheses. Well, we have to think about our assumptions in this case. And this is, again, something that's interesting about this hypothesis test. It's not strictly mechanical. There's going to be a lot of human interpretation and judgment in this, and this is something that's important. And again, I want to point this out. So we have to think about some assumptions. We've got to identify the probability distribution and the test statistic to be used. And then we're going to determine this level of significance. So next, once we've done that, we think, okay, this is what I want to test. I want to test it at this level of significance. How picky do I want to be? And then once we do that, well, we go and actually collect our evidence, right? We go collect our data, and then we just simply calculate the value of that test statistic. Okay, we've got that test statistic in hand now. So, well, we'll calculate that p-value from that. And then we're going to just simply ask ourselves whether or not that p-value is smaller than our level of significance, alpha. And based on that, we'll have some results. So, okay, let's do this, Patrick. Well, let's talk about writing this null and this alternative hypothesis, this null and alternative hypotheses first, because, well, that's where we're going to start. So let's look at an example, and we'll look at a couple other examples as well. So maybe you work at a company, and that company needs to buy some bolts for construction, and one of the required specifications is that the mean shearing strength of all bolts, mu, is at least 900 pounds, right? You're in charge of buying these bolts. You're going to build something. They've got to be sufficient strength. is the idea here. Now you're concerned, right? You're the boss man or boss woman is saying, hey, you go buy those bolts, make sure they're good, statistician. And you're concerned you might be getting bad stuff, and you don't want that, right? That's your job. Make sure that your company is buying good quality stuff. So you're worried that that mean strength might be less than 900 pounds. That's your concern, right? So there you are thinking about all of these things. Now, why can't we simply just go and test the bolts, right? There's situations like this. You can't test the bolt to see where it fails, because once you know where it fails, well, the bolt is broken. It's no longer, you can't repair it and use it again. So in this case, we would have to take a sample, and then based on that sample, right, based on that sample, we're going to make a judgment about all of the bolts. Okay, so I've got our steps written down here. Let's go through it. So we said we want to talk about that population parameter. So here that population parameter of interest is the mean mu. It's going to be the mean shearing strength of the bolts. That's what we're interested in. Okay, so we have to formulate our null hypothesis and our alternative hypothesis. And I've got these listed as number 1 and number 2. I'm not saying number 1 is the null and the second one is the alternative hypothesis. I'm just saying we do have to state those, and here are our 2 statements that we're worried about, right? I mean, these are the things we're concerned with. This is your concern, that the mean shear strength is going to be less than 900 pounds. And we write that by saying that mu, the mean, is less than 900. That's what we don't want to happen, right? We've got bad bolts. And then the other opposing statement is that the mean shear strength is at least 900 pounds. That's what the manufacturer says. They say, yeah, that bolt strength is they say it is 900 pounds. Well, if it's bigger, right, that's no problem either. It just means it's a little stronger. So that's the claim of the bolt seller, that strength is 900 pounds or greater, that shear strength. Now, there's a few different ways to state this null and alternative hypothesis. So for our null hypothesis, we could look at our mean, and we could look at it and we could think about that being greater than or equal to some value. So if our parameter, we want that to be greater than or equal to some value, the alternative hypothesis would have to be, well, if it's not greater than or equal to, it would have to be less than. And likewise, well, let's see. Suppose it's not less than or equal to, well, the other thing that could happen is it would have to be greater than. And last but not least, what could happen? Well, we could have our parameter equal to some value, and if our parameter is not equal to that value, well, that's the alternative. It would be not equal to it. One of 2 things happens. It's either equal to or not. It's either less than or equal to or greater, or it's greater than or equal to or less than. It sort of splits everything up completely. A little remark here that's important. This equals, right? We've got this equal to, less than or equal to, greater than or equal to. That equal to part of the statement, that's always part of the null hypothesis. So do keep that in mind. You want the equal sign to be incorporated into the null hypothesis. Okay, so using this little remark, in this case, we're going to have our null hypothesis. The null hypothesis, which is the claim of the bolt maker, that's that the mean is at least 900 pounds. It's 900 pounds or greater. So that's going to become the null hypothesis because, again, we have that equal sign included. If it equals 900, it's good. If it's greater than 900, it's also good. Greater than or equal to is good. And by default, that's going to give us our alternative hypothesis, and that says that the mean is less than 900 pounds. Again, that's your concern. Now, a little remark. We've got this null hypothesis and this alternative hypothesis. These can be rewritten as follows. So sometimes you may just write that the null hypothesis, for example, is that the mean is equal to 900, and that the alternative hypothesis is less than 900. So notice we have the same alternative hypothesis, but it doesn't look like the same null. When you see this equal sign, if the other part, for example, is less than, what it really means is that that first part incorporates not just equals to, but greater than or equals to. Personally, I'm, not a statistician. This is not what I do in my daily life. I've taught it quite a few times. I absolutely prefer this first set of notation, but I'm sure there's a good reason for this other one, and maybe somebody in the comments can tell us. So I just like this first description. To me, it gives me more information. But again, once you do a couple, you'll realize, hey, it's all the same thing. So maybe it's no big deal. Okay, so that's going to be our null and our alternative hypothesis that we're going to be testing. So let's look at a couple more examples of writing null and alternative hypotheses before we actually do this example. I know you're like, darn it, Patrick, let's just do this example. I just want to do 2 more examples of writing these null and alternative hypotheses, and then we will complete that. So suppose you're studying pollution in your city, and you're concerned a particular pollutant has a mean level higher than 3.6 parts per million, and that's determined to be an unsafe level. So what things are you going to study? You want to think about both the null hypothesis and the alternative hypothesis. So we've got these concerns, right? We're worried about, okay, so there's one concern is that the mean, let's look at this one. There's one concern that the mean is greater than 3.6. That's one concern, right? That would be your concern. And the other option would be, well, if it's not greater than 3.6, again, parts per million, it's going to be less than or equal to 3.6. Well, we want the null hypothesis to include the equal sign. So our null hypothesis in this case would be that our mean, mu, and that's going to be the this level of this pollutant, that's less than or equal to 3.6 parts per million. And at that point, that would be deemed safe. Likewise, notice what we said a second ago. We could write this by simply saying mu is equal to 3.6. Now, the alternative hypothesis, which is what you are concerned about, right? Maybe you live in this city. You don't want to be breathing in this polluted air. You're concerned that average is greater than 3.6. So that would now be your null and your alternative hypothesis. And again, sometimes you'll see it written like this. So that we've got our equal sign. They'll put off to the side. They say, oh, oops, really we mean less than or equal to is what we mean. So you may see it written this way quite often. Okay, so that would be our null and our alternative hypothesis. Let's look at another example. Suppose maybe there's a large factory and it wants to measure job satisfaction of its workers. So a questionnaire is given in the hopes that the mean score would be different from the past score of 65. So that past score of 65, it tells you something. Maybe they're happy, maybe they're not, maybe they're in the middle. And you want to determine, well, are they happier or maybe are they even like less happy now? You want to know 2 things. So the concerns here are, well, is the mean still the same, right? Does the mean still equal, would we say, 65? Or does the mean not equal 65? Those are the 2 things that we're concerned about in this case. Well, the part that includes the equal sign is clearly the first part. So our null hypothesis would be mu equals 65, the mean. And our alternative would be when the mean simply doesn't equal 65. Now, this is what's known as a 2-tailed situation. So when you have an equal sign and a not equal sign, that's going to go with a 2-tailed situation. When you have these null and alternative, when they're less than or equal to and greater than or equal to less than, those are going to be 1-tailed. And again, we'll see some more examples of these. But in this case, that would be both our null and our alternative hypothesis. Okay, drum roll, right? So let's get down to the nitty-gritty. So I'm going to go through the steps. It's really, the procedure itself is honestly not that terrible. But there's a lot of things to think about. So let's go back to our bolt example, right? Let's use that one, and we will do it to quote-unquote completion. So you've got to buy these bolts. You've got to make sure that the mean strength is at least 900 pounds. That's what has to happen. That mean has to be 900 pounds or greater. And suppose that we know that our sigma value in this case is 16. We'll make that assumption. So we've already stated our null hypothesis and our alternative hypothesis. So I've jotted those down again. So our null hypothesis was that the mean was greater than or equal to 900. That's what the bolt maker claims. And the alternative is that it could be less than 900, which is what you're worried about. So now we've got to think about these hypothesis test criteria. There's some thinking going on. It's not mechanical. So we have to check the assumptions and identify these assumptions. And this is something that through experience, a statistician or someone doing this in the quote-unquote real world would gain. Okay, so we know that sigma is equal to 16. Again, oftentimes we don't. There's ways to get around that. We will address that in a different video. So to me, I would assume that the shearing strength would have a mounded distribution, maybe approximately normal, right? I would expect the shearing strength of a manufactured bolt to all be, by and large, close to some value. Maybe there's some outliers that break really easily and some that are really strong, but I would assume that for the most part, they should be pretty consistent if we have a good manufacturing process. This is something I have to think about. Now, that's the size of the sample we're going to take. Maybe it's expensive to test bolts, and you don't want to take a bunch. Maybe you don't need to take a bunch. Maybe it's cheap to collect bolts and to make them and to break them, so it's no big deal to use 5,000 bolts, right? It doesn't matter in that case. This is something that you're going to have to make a judgment call. A statistician would have to make a judgment call. So we're going to use n equals 50, not a large amount, in the hopes, again, that the central limit theorem is going to apply and that the sampling distribution is going to be normally distributed. So these are some assumptions we're making. As I say here, you have to think about this because perhaps the thing that you're considering, maybe you have reason to suspect that maybe it's not mounded or normally distributed. Well, in that case, you're going to have to do something else. And a lot of times you're going to have to collect more data, right? More data is always good. So this is something that you have to think about. You can't just go through this mechanically, right? Okay, so what are we going to do? We're going to compare the value of the sample mean, that's what we're going to compute from our data, to the value of the population mean as stated in the null hypothesis. So we're going to look at what our data says, and we're going to compare that to our null hypothesis and see if they jive, right? Okay, so we're getting close. This is going to be the test statistic that we use. So this is important. If you're one of those people down there watching a video and taking notes, definitely put this little Z star in your notes. And you should have, again, seen this at some point when you talk about normal distributions and computing Z-scores. If not, certainly look at it because I will not completely rehash it, but we will talk about it. So we have that our Z star, that equals X bar, which is our sample mean, minus our mu. And again, our X bar, we're going to compute that from our sample, minus our mean mu. That comes from our null hypothesis. Now, we divide that by sigma divided by the square root of n. Sigma, okay, that's given to us, and we pick the value of n. So all of these values we're going to have. We can compute those. Well, next, excuse me, we have to pick this level of significance alpha. Now, again, this is yet another judgment call. Okay, so what does this level of significance alpha have to do with? Well, recall it has to do with the probability of us making a type 1 error. And a type 1 error, that occurs when a true hypothesis is rejected. So our null hypothesis, again in this case, was that the shear strength is at least 900 pounds. If we reject that, we're going to say, no, that shear strength was actually less than 900 pounds. is the conclusion we're going to come to if we make a, where do we go? If we make a, sorry, if we make a type 1 error. There we go. We're going to reject that null hypothesis. And in this case, that's going to mean that we reject a shipment of bolts that does or do meet the specs. Those bolts should have been fine. We should have collected the data and said, hey, these are good. But unfortunately, we made a type 1 error. We said, no, they're bad. We won't buy them. Now, how important is that type 1 error? Again, this depends, right? You know, maybe you needed these bolts urgently. Maybe you needed them like yesterday. Or maybe you can wait. You know, maybe if you needed them like yesterday and they're super important, maybe you don't want to accidentally reject a good set of bolts, right? Maybe you don't want to do that. So you think, well, should I adjust my level of significance? Or, you know, maybe you're trying to land this major contract and you want to be really, really, really picky about the quality of those bolts and you want to make sure they're perfect. Okay, and so maybe that would weigh into your significance. And, you know, there's a couple other situations that may apply as well. So I'm just saying it depends on the situation. And again, it's a judgment call. Typically, we again use alpha levels of 0.05 or 0.01. Those are the typical ones. So you will often just use one of those. Again, you just get to pick one of those. So suppose we make this judgment call and we say we pick this level of significance alpha equals 0.05. Okay, so now we go out there and we say, perfect, let's do this. We start collecting data about our bolts. So I go out there and I break a bolt and it breaks at a shear strength of 897, and then the next one's at 920 and 901 and 898 and etc. And I collect all of this data and I get 50 bits of data. Right? That's how many we decided we would collect. I've got 50 bits of data. Well, now I'm going to collect the test statistic. Well, we have to find the average. Now, I picked this number at random, well, to make my math work out. So I obviously don't have all 50 of these numbers right now. Suppose I do collect 50 sets of data. I add all of those sets of data, all of those values up. I divide that by 50, and I compute my average bolt strength to be this number, 89.6. Now, intuitively, right, your concern is that the bolt strength may be less than 900 pounds. Well, clearly 896.6 is less than 900 pounds, right? So that's clearly less than, but is it small enough to be of concern? I'm doing a little hand waving here. That's kind of the question is this number, right? Because it's clearly, again, I'll say it again, it's clearly less than the 900. Is this small enough to be of concern? And that's what we're going to address here. And again, that depends on your level of significance. So let's compute this test statistic. So there it is. So in this case, we set our X bar. We went through our data. We found it. That's 896.6. We subtract away our mean, and that comes again from our null hypothesis, which we said that was greater than or equal to 900. So that's our value, again, of mu. So let's go down there. We'll compute that. So 896.6 minus mu, which we said is 900. We're going to divide that by sigma, which we said was, 16, divided by the square root of n, which we picked to be 50. So you'll do this arithmetic, and I got this to be really close to negative 1.5. All right, negative 1.5, that's nice. So now the question is, what do we do with this number? Well, we're getting close. Negative 1.5. So now what we're going to do is we're simply going to calculate the p-value of the test statistic. So how do we do this? Let's talk about that. So the probability value, or p-value, what is that? So the probability that the test statistic could be the value it is. So how likely is it that we got that 89.6? Or is it a more extreme value in the direction of the alternative hypothesis when the null hypothesis is true? So again, this is just another way of saying what I said a second ago. 896.6 is clearly less than 900. But is it bad enough? Is it far away? Is it far enough away from 900 to be of concern? That's in essence what this statement is trying to encapsulate. Okay. Well, so what we're going to do is we're going to talk about let's talk about the standard normal distribution and that value of z star. So I've got my little standard normal distribution here. And what I'm going to do in this case, so this is the important part over here, to find the area that represents the p-value. So again, we want to find this value for the p-value. We're going to look at the sign in the alternative hypothesis. Okay, so the sign in the alternative hypothesis was that our mean was less than 900. Now, our test statistic, we got that value to be negative 1.5. So there that is on our normal distribution. Our alternative hypothesis, notice it's less than. That's going to be the part that we shade under our normal distribution. So I'm going to be concerned with computing this area to the left, the less than part of our test statistic. I want to know what is that area. Well, to do that, we'll just simply, again, we can use, to find that value, again, this comes from tables. This is stuff that you should have seen in a preceding section. We're going to find the probability that z is less than negative 1.5. And again, you can do this on a calculator or a table. I got that this area, this little shaded area, to be 0.0668. Okay, now this is going to be an important value. Now notice if our mu had been greater than 900, we would have computed, we would have been finding this area instead. So do be careful about that. So the area you shade comes from your alternative hypothesis. It's less than 900. We're going to shade less than that z star value, and we're going to find that area. And that's going to be our p-value. Almost done, my friends. The big question, is the p-value smaller than alpha, your level of significance? Well, since our p-value is not less than our level of significance, we can now make our result here. Okay, so this is our conclusion, sorry. So we're going to state this decision about our null hypothesis. So this is the question. Is the p-value small enough to suggest that the sample evidence is highly unlikely in the event that the null hypothesis is true? Again, is it far enough away to be of concern? In essence, again, I'm hand waving. So this is, to answer this question, we're going to use this decision rule. So one more thing, the decision rule. So if the p-value is less than or equal to the level of significance alpha, then the decision is we reject that null hypothesis. Okay, so if the p-value is smaller than the level of significance, get rid of that null hypothesis. If the p-value is greater than or equal to the level of significance, fail to reject the hypothesis. We're going to hang on to that null hypothesis. Well, in this case, again, we computed our p-value. We got this 0.0668. Well, that's greater than our level of significance. So criteria B is going to happen. The p-value is greater than our level of significance. Therefore, we're going to fail to reject the null hypothesis. So finally, the boss says, hey, what's the conclusion? So we're going to say at this alpha equals 0.05 level of significance, we're going to say that there is not sufficient evidence to show that the mean strength of the bolts is less than 900. So even though that average we computed is less than the manufacturer's claim of 900 pounds at least being the strength of the bolts, we're going to say, no, based on this level of significance, yeah, it's a little lower, but it's not enough to worry about. Go ahead and buy them. Go ahead and buy them. That's what it says. That is our conclusion. So that's what happens, right? You go out there, you buy the bolts. The boss says, all right, good job. We're going to go build our bridge. And then you've got the happy person on the bridge, right? Because most likely those were good bolts. So that is now the end result. So let me summarize this really quickly because we've talked about a lot of things that are important, but let's just go through it really, really, really fast to summarize. What do? You've got, okay, so we're going to, in this case, we're assuming we know our sigma. You've got some value of mu that's under discussion. You have to form your null and your alternative hypothesis. Now, based on that and the situation at hand, we're going to pick a value of n. How big of a sample should we compute? Well, you compute that sample, okay? You compute that test statistic using all of that information. We have to pick a level of significance. How concerned are we about making a type 1 error? Well, we now go and collect our data. We collect that. We compute our average from that data. We compute our test statistic. We get that value. We have to compute that p-value, again, based on the normal distribution. And depending on the null hypothesis, that tells us for a one-sided or one-tailed example like we're doing here, it says, do we look at the area to the left of that test statistic, or do we look at the area underneath the curve to the right? So we determined in this case that we need to look at the area to the left. We'll calculate that p-value using a table or a calculator, for example. And now we simply compare the value of the p-value to our alpha. And based on that, we make our conclusion. In this case, again, we said we would buy those bolts. We do not say we accept the null hypothesis. All we say is we don't have enough evidence to reject it. We don't have enough evidence to say that those bolts are bad, is the conclusion. Whew, okay. So in the next video, I will do a two-tailed hypothesis test. We will skip a lot of the nitty-gritty. I will just jump into some test statistics. I'll rehash a little bit of this, but we will certainly step through the next example much faster. I do hope this helps. As always, please feel free to post comments, questions, thoughts, all that good stuff. And if I can't help you, hopefully some kind person out there can point you in the right direction. All right, good luck, my friends.